So this week, last week we talked about the, oh, apologies, I won't say another word for a few seconds. Anyway, last week we talked about the origins of the universe, and we covered that ground a little bit today, but now we're talking about the origins of stars, and how did the first generation of stars form? What were the forces that led to that? That's actually what the James Webb Telescope was all about. At least half of the funds that went into it, design of the telescope, so that you could look way far back in time, way back past, past 13 billion years, and into the hundreds of millions past that. And Hubble was unable to do that. So what we're going to talk about today is the birth, life, death, and rebirth of stars. So that's a recurring theme in most creation stories. There's a birth, there's an interim, there's a death. In some fashion, there's a rebirth, or a continuation of the story into later generations. Not necessarily the individual, but a recreation. Well, it happens in the universe. Except that we don't know about the birth, interim, and death of our universe, or what might have preceded it and what might follow it. And we'll never know that because of the time involved. So we'll talk about the eyes on the universe, Hubble and James Webb, and the telescope and nurseries for stars. So let's just move along. Well, here we are. I already showed this slide last week, but Hubble, we owe a whole lot to Hubble, don't we? It was around for almost 30 years. It's soldiered on. It's created much of the understanding of the universe that we have. It had some other satellites, but it probably has been the most important. But it couldn't look far back, really far back, because it was designed to look at or capture light, visible light that we can see. But as the universe expands, light is stretched. The wavelengths become longer and longer into the red and infrared range, and longer still. And so Hubble was blind in the area that they wanted to look. And so Hubble was designed to detect infrared radiation. That's what it was designed to do. It's true that in the funding for it, there was a kind of a push. The other half of the James Webb Telescope was to look for early life. But as far as science goes, that's really not where the push is. Yes, and certainly get a lot of time looking for exoplanets. We'll talk about that a little bit later. But so Hubble and the James Webb Telescope. Now, I think I've already said some of this. It has a resolution, the James Webb, 1,000 times greater than Hubble. It's really interesting if you see pictures taken by the James Webb Telescope of exactly the same space in space. And boy, it's just like somebody fine-tuned the picture, and you see a lot more. And we're going to see a lot more as time goes by. It's interesting, the person who ran, John Mather, is a senior astrophysicist, got a Nobel Prize in 2006 for his work on that primordial afterglow after the universe began, after the Big Bang, which developed about 400,000 years after the Big Bang. It was a time when the universe had stretched an enormous kind of distance, but it also cooled down a lot. It cooled down to the point where electrons and protons could actually join and form atoms, and where quanta of light could actually escape. Now, of course, we don't see that light. What we see, the universe has expanded, stretched that light out into the radio wave, microwave range. So, I'm repeating myself there, but anyway, that's what he got his PhD for, that microwave radiation. That's one of the best pieces of evidence, hard evidence, for the Big Bang theory. You have to realize, that there was a lot of resistance to the Big Bang theory right up to the middle part of the last century. And anyway, so what does he say about this? Tell us about gravitational waves. Well, it's another, the first Nobel Prize in physics that I discussed here was in 2017. It was 2 years after the first detection of gravitational waves. Einstein had, it's a general relativity suggests, if you look at it, that if really massive objects collide, they'll create ripples, like ripples on a pond in space-time. And they should be detectable. Now, he knew about that. It was pointed out to him that it was one of the theoretical possibilities. He thought, well, the signals would be far too small, you'd never detect them. Well, they detected them in 2015 with two devices in the United States. Picked up the same signal, showed the same evidence. Now, those signals are really, really tiny, but the equipment was really, really sensitive. How sensitive? Well, the device for picking this up, which you'll see a little bit later, involved two arms, each 4 kilometers long, at right angles to one another. So these gravitational waves wouldn't strike each arm at quite the same angle. So one arm might lengthen relative to the other. How much might it lengthen by a proton over 4 kilometers? We're talking about really super sensitive equipment to pick these up. And then they were converted into a sound signal or a chirp, beep, like that. And that was the gravitational wave. So we're going to talk a little bit more about that later. So let's go on. Well, first dividend from the James Webb Telescope. Realize, when we look up in the sky, the dark sky, if you can find a dark sky, we see the little kind of twinkling stars, but we see a lot of darkness. And we assume there's nothing there, but there's a lot there. It's crowded if you had the tool to look for it. This is an infrared picture showing if we hadn't used an infrared lens here, it would all kind of look like this. So what is that? Well, we're going to talk about those. Those are vast clouds of various elements formed in the Big Bang, or maybe somewhat later. But so empty space is anything but empty. Now, well, here we are, interstellar space. There's these vast clouds, and they're not filled with kind of the molecules of life, as we would think about it. It's a little more primitive than that. But it does show, that number one, the central atom in life is carbon, and there are a lot of simple carbon molecules out there in those vast clouds. And so those are kind of little building blocks for life. Now, there are not a lot of them, but if you consider how big the universe is, there are a lot of them altogether. There are these gigantic molecular clouds that contain hydrogen, lesser amounts of helium, and a bit of lithium. And those clouds are the nurseries for stars. They contain what is needed for the creation of the first stars. So, we'll just swing along here. Now I kind of like this when I get somebody. This is a professor, a woman, who wrote quite an interesting article in Scientific American. So I just kind of just read this a bit. But bits of stars are all around us. We're not aware of that. And in us, too. We are made of stardust. We are wearing stardust if we're wearing gold or platinum. But we are made of stardust. in those clouds are some of the elements that will lead. Even after the Big Bang, hydrogen was there. That's a key. And of the seven elements of life, which we'll talk about later. So, so here's another picture of one of these vast clouds. And before the James Webb Telescope, you wouldn't see these kind of fuzzy areas here. You'd see the kind of the stars. The picture would look more like this, only you wouldn't see as many stars. But these webs all contain those very simple carbon molecules, but an enormous amount of hydrogen, and about 75% hydrogen, and around 25%, almost 25%, is helium. So that's what that kind of web is. One thing you don't see there is dark matter. The matter that we think about, the hard stuff, us, the furniture, all that kind of stuff that we look at and think of as matter, that constitutes only about 5% of the universe. 6 times of that is dark matter, meaning it doesn't interact with the electromagnetic spectrum, so you don't see it. Yet its gravitational force is much more important than matter itself in shaping star formation. Okay? And 2/3 of the universe is energy. That's dark energy. All right? So that's a little perspective. Now, Alan Lightman, now here's the recap. This is this interesting fellow at Harvard who has this joint appointment at MIT and Harvard, and Harvard, I think both of them. And he teaches in both faculties, and physics half the time, and some art subjects the other half the time. But it's a very creative thing to do. He certainly has the background to do it. So, how did he put this together? And well, he said the universe began with he called it a fantastically dense nugget of pure energy. In other words, what was there at the beginning? Not matter, energy. All energy. And then in less than a second, actually a trillionth of a second, the universe inflated at much more than light speed, many times light speed. And within literally a flash, shorter than a flash that we would think of, the universe was already at the edge of the visible, what could be seen anywhere. It was huge. And that played a very important part of things, because some people think, it's very hard to prove this, that in that before the Big Bang, or at the moment of the Big Bang, but before the big shock wave, the blast, the expansion, the inflation, that energy was quantally distributed, meaning randomly distributed. So a little bit more here, a little less there, but this variation, it wasn't uniform. And when it rapidly advanced like that, that variation was carried through the whole universe. So you had a quantum universe at the very beginning, translated in less than a second across an enormous distance in the universe. Why is that so important? Because if matter or energy is uniformly distributed, gravity can't act on it. You can't create stars. Matter has to be kind of clumpy, unevenly distributed. And so it was unevenly distributed. That made it possible for the force of gravity to clump it even more and begin to form these primordial clouds and denser and denser clouds, and they started swirling around and around, and then you begin to get what looks like the beginning of a star, a sun, no light yet. And then it becomes increasingly dense, more and more dense. It's made up of hydrogen, almost all hydrogen and helium. And the force of gravity compresses it, becomes more dense, hotter and hotter, until the point fusion ignites. And now two atoms of hydrogen combine to form helium, and in the process release an enormous amount of energy, a huge amount of energy. That's where the light came from, stars, because those quanta of energy made their way out to through these giant stars to the surface, where they lit up the universe. They were very, very bright, extraordinarily bright. There wasn't kind of the mess up there. I mean, there's certainly the clouds of stuff, but those clouds would grow with time. So, he says, after the first 3 seconds, all the particles and forces appeared, and then I mentioned this earlier, this cosmic dawn. 400,000 years later, the universe had cooled enough for the simplest atoms to actually form, and for the light quanta to be seen or picked up as this cosmic background radiation as the most important evidence for the Big Bang, experimental evidence. One thing you should know about the evidence for the Big Bang and almost all of the events that we talked about last week, we're talking about this week, it's really a combination of mathematical modeling and experimental evidence. The cosmic background radiation is the evidence, something you can actually measure that is consistent with the predictions of the mathematical models. So this story we're telling here is a creation story, in a way, of theoretical physicists and experimentalists coming together. So that's what's happened. So let's move along, and we'll see where this little story goes. Well, Alan Lightman talked about that. Well, I've already said most of this. So sometimes I use slides just as a reminder for me, so I don't lose my way. Not necessarily because I expect you to read them. So I'll just go on to this next one, because this is really, in a nutshell, AllStars form. So birth begins with these variations in the density of matter in the early universe. I said it was a quaffle, suddenly spread throughout the universe, carried out. So in the macro world of the universe, those variations were retained. Gravity began to shape these uneven clumps of matter, hydrogen, some helium, into increasingly dense collections of gas, and as I said, beginning to spin tighter and tighter and tighter. It's like when you flush the toilet, it goes like this, or a load, that kind of thing. Tighter and tighter and tighter, more and more matter clumped together, more and more dense, then the formation of a star. Some of those stars were giants. Look at that, hundreds to thousands of times the size of our sun. Our sun is actually a piddly star. It's on the kind of the low end of the range. And now, when these stars have some of these stars were most of them were giants. They were extremely hot. The light was very bright, but they were, most importantly, they burned through their nuclear fuel of hydrogen very quickly. So our sun has already lasted, probably 8 billion years, something like that, around there. Our sun is the third sun in our region of the Milky Way. Third generation star. The other two have passed before they've gone through gas.
I just wanted to ask you something. All of this is happening while the universe is expanding, right?
Yes.
So I get in my head, we're expanding it, gravity is pulling stuff together, so is there not a conflict between
Well,
the
you're,
expansion of
well, I
taking
see what
place?
you're getting, kind of diluting the matter.
Yes,
But gravity,
time gravity is pulling it back.
hold all this stuff early enough, and what I can't show you is dark matter. Dark matter and very early, large, gigantic black holes form not long after the Big Bang. And their gravitational pull helped to shape the formation of stars. But you're right, the universe is expanding like crazy, and still is. It's accelerating. Yeah, so it's a good question, actually. Now this is what an artist, I mean, maybe the James will get lucky, and the James Webb Telescope will actually show us an early star. Now understand, it's not showing us that star in real time, right? We're seeing stuff after it's traveled 13.6 or 7 billion years. That's what we see now. Those signals have traveled through space at the speed of light. It takes a long time to get here. So when we look at anything in space, the further out we look, the further back in time it is. So events so you're looking at stuff, I mean, heaven knows what actually happened to some of those early stars. Well, we think we know what happened to some of them, but we wouldn't actually see it unless we were around at kind of a little later time to see that stuff arrive here. So we're looking, as I said, we're looking at old stuff, old signals. I mean, it takes, around 8.5 minutes for light to come from the sun to us. That's a very short distance. So it takes a long time. So we're looking long, way, way back. Now, the creation of the element. Now, one of the keys, and interestingly enough, a Nobel Prize was not awarded for this, it should have been, because the stars, they don't last forever. What tends to happen with stars is they burn through their supply of energy, most efficiently the hydrogen. And when they do, all of that heat and energy that is created through nuclear fusion kind of dies down. So the expansile force, the heat and energy generated by the fusion, that diminishes, and the star begins to collapse. The core collapses and the other layers collapse, and they smash into one another. And when they smash into one another, sometimes there's a temporary period when the temperature suddenly spikes and that kind of thing, and more elements are made. But prior to that supernova event, which we're going to talk about, and you'll actually see one in a moment, there's a period. Those early stars those giants were probably capable of creating most of the lighter elements. Those are the ones that we're composed of, meaning hydrogen, carbon, nitrogen, phosphorus. There should be 5, probably left one out. But anyway, those are the life-friendly elements. They're all lighter elements. And they would probably have been formed in the crucible, the core of those early stars. And when those stars, if they did explode, and a lot of them did, those newly formed elements were then scattered through the neighborhood to be picked up and clumped by gravity again, and forming a second generation star, and a third, fourth, whatever. So that's what happens. Now, as it turns out, I'm kind of skipping ahead of some of this material, but that's all right. About as far as you can go in a first or second generation star is to iron. By the way, you may or not know it, but the core of this planet is iron. There's a solid iron, hotter than double at core of this thing, and it spins. It rotates. Then there's a motor outside that moves in the opposite direction, believe it or not. And so iron is the limiting element for the kind of steady formation of elements in the core of stars. Creating heavier elements than that by the usual process doesn't create enough energy to actually carry the process further. It takes too much energy, almost too much energy to make iron. And anything heavier than that is almost impossible to do without finding another source where they can really kind of boost the temperature and the pressures, which is what happens with supernova events, these explosions of stars. Then you can kind of create the heavier elements. But even then, for the heaviest elements, it requires the collision of two neutron stars, stars that are primarily made of neutrons. And they're extremely dense because there's no polarity to them. It's not like bringing protons together that kind of push each other away. Neutrons have no charge, so they can really jam up close to one another, such that, for example, the mass of the sun might be compressed to something the size of Manhattan. That's a common analogy used. So really, really dense. It's with those collisions, I'm getting well ahead of myself here, but in those collisions of neutron stars, that the heavy elements, gold, platinum, tungsten, those elements are created. But for most, it's up to iron and no further, unless they explode, unless they collapse. So let's see. Well, here's one supernova that was caught, and there it is, right there. But we'll just have a look here. Here's one. And actually, the beginning of it, so we can watch this again and again, but this thing, yeah, that's the beginning of it here. That's the core collapse, right? Things are collapsing in the core, and the outer layers collapse in on that very dense core. It creates a huge shock wave that goes through the dying star. All the outer layers, the middle layers, are shattered, dispersed throughout that area of the universe, and so it leaves a very dense core, often a neutron star or a black hole, and then all of these elements beyond iron, as well as up to iron, scattered in the neighborhood. And it also creates, particularly if one or two of these things, these stellar events actually collide with one another, it creates an even more violent reaction. And this would, even a single explosion in one star, something like this, would create gravitational waves that could be detected. They haven't been detected from a single such event yet, but they could. So that's and sometimes you get weird kind of things like this where they get these, it almost looks like somebody blowing smoke, you get the rings in here, but these are rings of energy that have been released by the supernovas right in here. And that's one ring, and then splitting up. So there's a directional part to it too. So it's quite beautiful, isn't it? Well, we talked about collision of two neutron stars. Well, middle and the bigger the star, the more likely the stars were to have formed as pairs. So if one star has collapsed and created a neutron star, sooner or later, the other one in the pair is going to go through the same process of collapsing, huge release of energy, and leaving a neutron star, so we have a pair of neutron stars circling one another. And the circling gets tighter and tighter until they slam into one another. When those gravitational waves were initially detected back in 2015, and really got the astrophysical world really excited about it, well, then they were looking at other objects. So the first detection of these gravitational waves followed the collision of two black holes, each of them with a mass of, say, 20 or more times the mass of our sun, so pretty big. But the black hole at the center of our galaxy, the Milky Way, is 5 million times the mass of our sun. Anyway, they did detect these gravitational waves, and then it wasn't long, I think it was less than a year, that somebody spotted a really bright event taking place and correctly interpreted it as a collision of two neutron stars, the densest objects in the universe, with a huge release of energy. And we're able to detect that, and sometimes a neutron star colliding with a black hole. So what's turning out is that these collisions happen all the time. It's like black holes. Until anyone really started looking, they thought that it wasn't until, 2019, we actually saw a black hole. And then the next year, a Nobel Prize was awarded. Stephen Hawking, unfortunately, dead at that time, or he would have shared in that prize, and it went to Roger Penrose and a couple of other groups. But anyway, but black holes were thought to be really uncommon. Well, they're actually dirt common. And some of them can be very small, and some of them just enormous in size. So, well, we've already talked about a lot, so that's just, I kind of like this story right here, because it's a nice one. It tells that this is a story written by, as you might guess, a physicist. So just follow me on here. So eons ago, a star more than 10 times as massive as our sun died in a spectacular explosion, giving birth to one of the strangest objects in the universe, a neutron star. We've talked about that. This newborn star was a remnant of the stellar core, compressed to extreme densities, where matter can take forms we do not understand. Most massive stars live in binary systems, I mentioned that, in pairs, with a twin. And the fate that befell the first star eventually came for its partner, leaving two neutron stars circling one another. As they drew closer together, tidal forces began to rip through the flaming neutron-rich material into space before they merged, sending ripples, gravitational waves, throughout space-time. At the time of the crash, this is the boggler here, at the time of the crash, our pale blue planet, in a quiet part of the Milky Way, about 130 million light years away, was home to the dinosaurs. So when these neutron stars actually collided, that's the thing. Far out, takes time, limited to the speed of light. So this crash actually took place a long time ago, at a time when the dinosaurs were around, but it took this long to reach us. Okay, you following me here? It was home to the dinosaurs, and the ripples of space-time, called gravitational waves, began making their way across the cosmos. And in the time it took them to cover the vast distance to Earth, life on the planet changed beyond recognition. New species evolved and went extinct. Civilizations rose and fell. And curious humans began looking up at the sky. They developed instruments that could do incredible things such as measuring minute distortions in space-time. Eventually, the gravitational waves traveling at light speed and the light from the merger reached Earth together. And astrophysicists recognized a distinctive glow that showed the presence of new elements. Now, that's incredible. That's a really good illustration of how long it takes. Events that happen, horrendous events, but if they happen a long, long time ago, it takes a long time to get here. And of course, you've got to be listening and looking to catch them. Now,
we think of satellites as going around in orbits. Some of these neutron stars have an orbital phase. They can bump into one another eventually, so they don't keep that separation the way satellites do.
no, that's right. Oh, so I just wanted to show you this gravitational wave detector because this is one there are two in the United States. They're being built in China, India. This one happens to be in Italy, but it shows those 4 kilometer long tracks, so the gravitational wave might come along, say, from this direction. And if it hits both of them, it'll hit this one kind of lengthwise, head on, and affect the distance here much more than this one. It's extraordinary that governments fund this kind of stuff. I mean, I'm really glad that they do, but it's amazing because where's the benefit if you're looking for us or for anyone else? I happen to be really excited about it, but these things, this gravitational wave stuff, this took 35 years in consecutive funding from I've forgotten how many presidencies, but anyway, 4 or 5 or 6 of them anyway, and different Congresses to provide continuous funding. Just imagine how difficult it would be to keep that up these days with the current climate. I mean, people in those days were really good about funding stuff that went beyond their term. Now, let's see. Oh, here's that. Now, this is an artist's conception, but those first 2 black holes circling one another, and here they are, the ones that presumably created that first series of gravitational waves that were picked up in the United States and won a Nobel Prize 2 years later. And the heaviest elements, I've already mentioned, they're created with neutron star collisions. Here's again another artist's picture of a collision of these new neutron stars, a pair of them.
Question.
Oh, here we go. Yeah.
It says in the southern constellation of something, who determines, that's all in relation to Earth, I assume.
It is all in relation to Earth, exactly.
Because in what direction are we looking to find the origin of the Big Bang from here?
Oh, that's a really interesting question, isn't it? Because the Big Bang, there wasn't any direction. It was on a direction. When the Big Bang happened, it went in all directions, 360 degrees all around, like something happening in the center of the Earth and going in all directions. But if you look at a lot of science texts and papers, they don't show it to you that way. They show it to you sometimes with something like this. There's that black pen they have here. There. So they'll show you the stuff, and it's quite common to see this, and it's quite misleading because it shows something that has a shape like this, and the Big Bang comes starting here, and then all events after, like this. Well, look at that. Well, what's going on over here? Right here. But it's very misleading because it suggests it's all taking place in a tube, and it's not how it's happened. It's happened at the center, and it's spread out from the center. And it's good, excellent question. Very good.
And just one more, and so
Yeah.
as the universe expands,
Yeah.
the planets in our solar system and the sun don't really change their relationships with each other, do they?
No, it's the galaxies that are, well, first of all, I think I mentioned this last week. None of these galaxies have an engine on them. They're being dragged by the expansion of the universe. Yes, they're moving relative to us. And the further away they are, the faster they're moving. But and they're moving relative to one another. But it's the expansion of the universe. It's like that balloon that I didn't inflate last week. It's like that balloon that you blow it up, and if you put little dots on it before you blow it up and watch it, all the dots start to spread apart. Right? That's what's happening. The universe is expanding, carrying everything out, but carrying whole galaxies. It's not, the galaxy isn't expanding. Individual galaxies are not expanding, but they are expanding relative to one another and the universe. Excellent question. Yeah, very good. Periodic table, you kind of recognize this, but I just yellow lined the elements of life here, where they are. And there they are. There's carbon, the matriarchal element, probably the most important element. It's a carbon-based. All life is carbon-based, right from the beginning. It's carbon-based. And all of those elements are very closely located here. And there's hydrogen over here. These are sodium and magnesium, potassium, calcium. There's iron that we were talking about, that kind of limiting one, but you really need a supernova to go beyond that in size. But they're all light elements. What does that mean when I say light? It means that they have fewer orbits around the nucleus. So the electrons are actually quite close to the nucleus. You know, it's a little like going into a theater at the Shaw, except the theater's on the round. And if the nucleus is at the center of that theater, and the theater's on the round, and you have a row of seats, and you climb up, it takes more energy, incrementally, quantum steps of energy. First orbit, second, third, fourth. So 2 electrons in the first orbit. The second can contain up to 8, and the third out 18, and so on. The reason why carbon is so key is it has 6. It has an atomic number of 6. So it fills up the first row of seats, 2 seats. Then it reaches the orbit that can contain 8, but it's only got 4. So there are 4 vacancies. Carbon wants to share electrons or borrow electrons from other atoms. So when you look at molecules, what you're really looking at is a marriage between different elements and sharing electrons. Each of them trying to fill out their outermost orbit as completely as they can. That's what's happening. In a nutshell, that's what's happening. And it's one of the reasons why carbon is so important to life, because it forms tight bonds, but not so tight that they can't be broken and kind of change things. Now, I'm not going to go through this again because we've done this, but here's the composition of Earth. There's the composition of the human body. Well, look at Earth. Here we are. There are 4 elements that kind of make up Earth. All the rest is kind of under 2% or 3%. But iron, that core I talked about earlier, solid core at the middle, and then the fluid part of the iron is moved further out, and then this huge expanse of silica, and then the crust. And we're living on the crust. Oxygen, one of the elements of life, silicon. The option to carbon. If you were building life, could you actually use silicon? Yeah, it's right. If I went back, let's see. Let's see. Oh. There's silicon right underneath carbon. So some people have speculated that elsewhere in the universe, life could be built. The matriarchal element might be silicon. There are reasons for not thinking that, very compelling reasons, but anyway, that's the possibility. So, now, we're not going to do that. Oh, back to these. Now look at the life elements here. Oxygen, big part here in the Earth, big part here. But carbon, hydrogen, nitrogen, calcium, phosphorus, those are the key life elements, the keys to life. And if you want proof of that, look at DNA. Again and again, what do you see? Oxygen, phosphorus, hydrogen, carbon, carbon rings, forming the basis of the bases here, sugar molecules, and phosphate groups on the outside. This is the outside of the ladder here, holding the bases together. They're the bases. All the work is being done really in between these. These are complementary strings of bases here. This is a DNA. But on the outside, like a ladder, holding it, that's helix together, are alternating groups of sugar and phosphate groups. But look at the elements. They're that biological, those elements of life, which formed relatively early in the universe. Possibly as early as those first stars. And then just scattered and then picked up fortuitously by stars forming. I like this one. This is one. Did you ever see that movie, Larry Crowne? Okay, well, watch it. Julia Roberts and Tom Hanks. But in the movie, Tom Hanks, this is a year's course on public speaking. And Tom Hanks is a student, Julia Roberts is running the show, so the last little speech he gives is on Earth and Bernard Shaw. He was expected to combine the two in 2 minutes. So we finished off with the first. George Bernard Shaw once put the fool's brain digests philosophy into folly, science into superstition, art into pedantry, hence a university education. And so I kind of like that. Now, we'll finish off right here because, and then we can talk to some questions, because this leads right into next week. What is the chance of life elsewhere in the universe? Well, as far as I'm concerned, it's very, very likely. Just look at the numbers. Because the study was completed by several groups in Europe and the United States working together, and some others, and they had very conservative criteria for what would be a habitable, possibly a habitable planet, meaning in that Goldilocks zone of temperature, a rocky planet in the right place for liquid water. 300 million in the Milky Way alone. 300 million possible exoplanets. When people talked about, with Hubble finding 2,000, it became 3,000, 4,000 possible exoplanets. By the way, a Nobel Prize was given for that discovery in the last few years. Those exoplanet stuff. But the studies were originally done in the late 1900s. But if there are a trillion galaxies, and now it would seem that that's closer to 2 or 3 trillion, just do the numbers, multiply them, look at the figure you get, 2 times 10 to the 19th. So even if the probability of life was something 1 in a billion, and a little perspective on this, we have not been around all that long. I mean, Earth has been around 4.5 billion years. Life in some form, identifiable form, possibly goes back to maybe, it's a stretch to put it up to 4 billion years, something like that. And not a lot happened for 3.5 of those billion years. It was a single cell universe on Earth. Now the cells became more complex. They became eukaryotes. They developed better metabolism, better energy systems. But if you were a visitor from outer space and looking around to see what Earth had to offer, you wouldn't find much. You'd find a planet full of little cells. And then the Cambrian explosion, over 500 billion years ago, 500 million years ago, that's where we all came from. That's when complex multicellular life began. And we're one of millions of products of that evolutionary process. So again, going back to that visitor from outer space looking around, they would have to be very lucky to catch the time now to be orbiting or kind of close to us and say, oh gee, look, there are animals moving around down there. They're on 2 legs. And they seem to have kind of changed things on the planet. And, but that's all very recent. I mean, if you visited Earth, say 120 years ago, it would be dark from if you were up on an astronaut looking down at Earth, you wouldn't see what you see now. All these cities lighting up. That's kind of well less than 100 years. That's 100 years in 4.5 billion years. And going further, as a species, we're kind of about halfway. If you look at all of our antecedent species, meaning our Homo earlier, going back say 2 million years to Homo erectus, antecessor, and I mean that's a short history. That's 2 billion years. And if you're going back to people who had sophisticated symbolic language, anything like us, probably 100,000 years ago. Maybe stretch that if you really want to stretch it, but there's no evidence really to support it. Going back over much more than that. So people like us communicating with one another in a complex fashion, we don't go back very far. And our predecessors seldom lasted more than 500,000 years, if that. They might last for a few 100,000 years, and then they morphed. I mean, it's a screwy thing to talk about species because it really depends on how long it takes for these anatomical features to kind of add up to be a named species. So that isn't actually how things happen. It's much more gradual. But the point is that species like us, we probably won't be around in 1 million years, or 500,000 years, or maybe even 100,000 years. Because unlike any of our predecessors, we have the power to actually do ourselves in, and every other life form, except those single cells. Because there are lots of places where they can hide out, a mile down the Earth, lots of space that they could. After all, remember, those single cells for much of their history survived in an oxygen-free environment. That was a later acquisition. So that's so these are all. So I like this one by Michael Shermer. What science tells us is that we are but one of hundreds of billions of species that evolved over the course of 3.5 billion years, stretched that on a tiny planet orbiting an ordinary star, itself out of possibly hundreds of billions of star systems. Well, see how the estimate went. Forgot the year he wrote that, but you have to go up into the trillions now. It's not hundreds of billions, but into the trillions here. Not so different from trillions of, oh, no, it's right. Not so different from trillions of other galaxies in an expanding universe that is very possibly only one of a near infinite number of universes. So on the last thing, when we get to the last, we're on the end of the second. The last one is on, well, what happens? And what do people think? I can tell you, experimental physicists love this kind of stuff. To speculate. And it's great. It's wonderful because they're testable hypotheses. Some of them are, anyway. How you would ever prove anything like Penrose suggested that well, we started with a singularity, something really incredibly dense, but it will return to something incredibly dense, and that will trigger another universe that follows us. In other words, we might be one of many universes along the way. It's an interesting thought, so we'll get to that later. But what I love about all this stuff is that people think big, really big. So it's very hard for me to, when I think about creation stories, some creation stories, even the science creation story, to think that this is the last chapter is anything but the last chapter. We're in kind of chapter 1, maybe halfway through chapter 1. But we didn't even have a prologue or an introduction 100 years ago. We're not much. So it's something to kind of think about. And you can see why, with creative imaginations that we have as a species, why there are so many creation stories. Creation stories are the default setting for humans as a species. As far as I know, and the historical record, there is no spirit. None of us existed without our creation stories. So that seems to be, we like to tell stories, and we like to hear them. And stories that, why would we go to the Shaw? Why do we go to the Shakespeare Festival? Why do we go to the theater? Why do we stream stuff? We're just watching stories in different forms. That's what we're doing. And we spend hours in it. So this is just another way of tying it together. So, any thoughts or questions?
I just wanted to ask you about the creation myth of the God that's always there.
Yeah.
I'm not talking about a transcendental God that gave everything a kick to start the energy, but the God that's with everyone. Yesterday, the Super Bowl, the football player that won it, Mahan, somebody giving credit to the God who was watching after him. This is an immanent God, and no politician ever get elected to as dog catcher if he didn't believe in a God that was there giving him direction. So that why are we as a community? Why are we why is it so necessary to have this mythology associated with the God that's not a transcendental God, but an immanent God that seems to be the one everybody refers to. I mean, that's a question. But you answer things very well with clarity. So I'm just saying, if you only just brief thoughts about why this is such a, in our society, knowing all of this that you've given us, and that we still cling to this as a species.
Well, it does seem to be a compulsion. I mean,
God bless America. You ever seen the president not talk about God blessing?
No, I haven't.
Is that sentimental language, or does he believe that? I don't know. No, you don't know either, but I'm just saying
I
that.
don't know. But
It's a superstition.
Well, maybe.
But I think there is a compulsion to gossip, to tell stories, to make stuff up, to enlarge stuff, make them bigger than they actually are, change the story. That's a very common thread through human experience. And so much so, some people have argued, well, is the brain wired for this kind of stuff? And, well, I don't know, and no neurologist knows, but it's very interesting. I had a conversation with somebody yesterday about that. I mean, the human brain is capable of great rationality, but it's also capable of making stuff up with equal skill, and maybe not equal time, because I think the making up takes up more time than the other. But I think the same brain combines those propensities, I think, so those kind of cognitive and imaginative skills. I mean, it's a wonderful thing in a way, but it's a paradox, isn't it?
So that people compartmentalize their.
Yeah, compartmentalized. And then you see somebody like Roger Penrose, winner of the Nobel in 2020 for black holes, where he divides the cosmos up into three kind of spheres. One is us, what we're used to every day. One is mathematics, he happens to be a mathematician, but I do understand why he would put that in there. Because math, put another way, precisely describes relationships like no other skill that we have. And then, consciousness. And I don't know what he means by that. I mean, but I don't know what he means. But I think.
But what I'm saying is, religion can have such a hold on. I have years ago a colleague, a very bright urologist who very scientific, do all his business. And when I was reading the Satanic verses at the time, and I said, "What would you do if Salman Rushdie walked into our change room here at the operating room? What would you do?" He said, "I would kill him." I said, "What do you mean?" He said the fatwa had been given by the person in Iran that this man was an infidel and should be. I said, this is a very rational person, very quiet, gentle, yet he would, because of this directive from his religious side, would have taken and actually attacked this individual. I mean, it was attacked. It was talked with this year, as you know, at that meeting, but there was that duality between his scientific side and this compartmentalized religious side.
I mean,
it shocked me because I couldn't.
But humans are capable of great humanity, but great violence.
Yes,
There's
for sure.
no other species as violent as humans, and in the same person.
Yeah, well, that's what this duality
I
here.
mean, how else do you train armies? And you train them to go and shoot the other guy or blow them up. It was no part of their life before. It's not going to be part of their life after, except for nightmares. But they're capable of doing that. Sometimes think about that. As I was watching with my grandson some months ago. He was very interested in what happened in Germany in the 1930s, and seeing these young guys, these godlike figures, blonde hair and that kind of thing, marching, swastikas on them, and SS.
Hitler Youth.
Yeah, Hitler Youth. And capable of incredible things, as it turned out. And Well, that's one of the paradoxes of humanity, isn't it? And the bad guys aren't always the other guys. Sometimes it's us.
Interesting, we've welcomed many of those same Hitler Youth back into our scientific programs in the U.S. and Werner von Braun,
Yes, we did. Yes, we did.
the rocket man from Germany, was largely responsible for the moon program.
Yeah.
Much of it anyhow.
Yeah.
He died as a hero in Florida.
Yeah. No, one of the reasons I put this series together was to provoke the kind of discussion that you've actually brought up. So it isn't just astrophysics here, but it does put it, the playing field has become much larger, much broader in time and spatially and in time. It's a much larger conversation. And in one lifetime, I mean, when I think back, I mean, I'm 83, but I look back, that's not even a century. But I think about all the language, it's on YouTube, but the shit that's happening, and that stuff in various places in the world. And just a small, not even 100 years. It's incredible. So what's happened, and where's the end of it? I don't see. It doesn't seem to be any. I do think one of the paradoxes of neuroscience, or the idea of the brain, is the brain's it's proven to be really capable of marvelous ideas, concepts, developing evidence, and developing tools, and much of what surrounds us are products of that. But I don't think the wisdom factor has gone up one iota. So you have one chart showing this for kind of innovation and tools and destructive tools at that here, and the wisdom level is down here. It hasn't changed. I might say from an evolutionary point of view, a rough look at the brain would suggest that those areas of the brain that relate to emotion and kind of feelings and control of those, that hasn't changed much. What's changed is the neocortical area that's related not just frontal area, but the temporal and parietal lobes, all of and that part of the brain. And the other thing is that until say 100 years ago or 200 years ago, where most of us might have lived in villages or towns, or if you were or on a farm. Most of Americans and Canadians lived on farms, and say pre-war, or close to that. Certainly pre-First World War. So who do you talk to? Your community is what? 50 or 100 people? That's what you hear about it. Maybe a newspaper, but probably not a radio yet.
And send it around the church often.
Yeah. So but now, I mean, kids through using the internet, you can access information that is would have been beyond our imagination at an earlier age. Yeah.
Misinformation, I mean, that's
and misinformation.
That's a very important.
But we can share information. We become kind of a giant brain, if you like. That kind of, I don't know what the rules are, but we pass information back and forth among us like crazy, with great facility, in a way that 100 years ago we couldn't, 50 or 60 years ago we couldn't do. And that's a real problem.
Maybe the wisdom line will start crawling up a little bit.
Well, maybe, but what's going to drive it? I don't think so. Anyway, so good stuff. So next week, I think it's black holes. Kind of prosaic. Okay. But then we get into some more interesting stuff. All right. Well, thanks very much.
Thank you.